Well, welcome to module number 4 in numeracy. We're talking about angles, talking about geometry, shape, and so on. So let's run a few angles over that. The language of geometry really does go on angles. And here's some of the classification of the different angles that we'll find in geometry. Acute, I say it's nice, cute, it's small, it's cute. Everything's right, it's square. Okay, and then the others, obtuse, greater than 90, straight is a straight line, 180 degrees. Reflex is bigger than that, and the full rotation, of course, the clock, for example, is 360 degrees. It's a circle. So there our language of the different classifications of angles that we will have. And the next point that we want to go through is how do these convert in terms of shape? So let's pull me over the side a bit there. Now, how can you see some patterns? Well, I can see one, this angle and the sum of the interior, so all the inside angles. So there's 1, 2, 3. We add them up, a regular triangle, not an equilateral triangle, for example, and each angle inside is 60 degrees. And the three of them together add up to 180. So I can see a pattern. 180 divided by 3 equals 60. That seems to make sense mathematically, doesn't it? So the internal angle of a regular shape, for example, in the triangle, is that 100. It's divided by the number of sides it has. Because there's three sides, 3 angles, 4 sides, 4 angles. And the same would go here. So 360 divided by 90, there's 4. They all align. Now, the interesting thing about is there a connection between the sum of all the interior angles, and then we add all of them up? Is there a pattern between them? So I have a look at here. They've all got 10s, haven't they? So is there a pattern of 10s going on? 18, 36, 54, 10s. How are they related? Let's start with a triangle and let's do the quadrilateral or a rectangle shape. So the sum of all the angles inside is 180 degrees. In the triangle and in the square, it's 360. 4 lots of 90. Okay, yep, I can see how that's a right angle, 90 degrees and so on. Is there a pattern there? And then a pentagon's 5. Are those 3 a multiple of anything? Well, if I looked at 360, how's that related to 180? Twice as long. Right, so 2 times 180 is 360. Great. What about 540? Is that related to 180? Well, 3 times 100 is 300. 380s are 240. Bang. 3 times. So 1 times 180, 2 times 180, 3 times 180. You guessed it. 4 times 180, 5 times 180. You sure? 500s are 500. 580s are 400. Okay, yeah, that's correct. There seems to be a pattern. So God designs everything so well, and mathematicians just find it out and try and classify things. But there is a rule. So it seems to be 3 sides, 1 times 180, 4 sides, 2 times 180, 5 sides, 3 times 180, and so on. So what is the area there? Well, there it is. If the number of sides is n, take 2 off and multiply it by 180. Let's try that here. 3 sides, take 2 off, 1 times 180. Yep. The rectangle, 4 sides, take 2 off, n minus 2, 2 times 180. Take 2 off, 3 times 180, and it works. And so to find out the measurement of the angle on the inside, well, let's take the, excuse me for my sneezing, the quadrilateral or rectangle. Well, if it's 360 on the inside, divided by 4 sides, there's 90 on each. So that's the n divided by n, remember n's number of sides. So there's some patterns and some rules you can play with your students in this regard. What's next? The next one is moving shapes, called translating shapes. Fancy term. Translation is moving. We're going to look at a couple of others shortly. Reflecting, like a mirror. And the last one, went too fast, is rotating, so it's on an axis. So we're going to look at those three things: translating, reflecting, and rotating shapes. Now, translating the shape is actually the hardest one. I don't know why we started here, but we did. So if you take that triangle and put it on a grid. So a grid sort of references it, and that's a Cartesian plane in a mathematical sense. So if we look at a point, we look at point B, and if we go and have a look at point B, the x coordinate always comes first. So it's -8 here, and it is 8. So B is -8. Yep, perfect. So how did I get B over to here? I moved it. Well, how far did I move it? Well, Cartesian planes are boring. Okay? There's one way of measuring it. You could say it goes so many centimeters at a certain angle. Yep, would be correct. Absolutely would be correct. But if we use the affordances of the Cartesian plane, in a sense, B went 1, 2, 3, 4, 5, 6, 7, 8 to the right, 9 to the right. So B went 9 places to the right, and it went down 1, 2, 3, 4. So I translated it 9 units to the right and 4 down. So what I've done, now I keep the orientation of the shape the same way. And so if B moved 9 right, 4 down, well, so did A. 9 right, 4 down, and so on. So we call them A prime. So translation is essentially going forward, is moving something 9 right, 9 units and 4, and perhaps going in a problem that goes in reverse, in the sense that if you've got, without telling you what the answer was here, if those are the points here, A and A prime, what did it do? Go from before and after, and you would work backwards, and you'd say, okay, I would pick again B, doesn't matter which points you use because it will be the same, and you'll work out, okay, here it's gone across the x-axis is always first, and up or down the y-axis, and that concept is called translation, and there's quite a number of videos on that. So how would you do this in the classroom? Well, you get some graph paper and so on. You can make it bigger if you wish, and you get, cut out some protractors so they get the concept of degrees. But let's look at translation. So let's put an object here, and say we're going to do a forward direction. So we're going to translate it and then see where it ends up. So the answer is, let's translate that to the left 8 and down 3. So we take point A, and we would go in the head, we tick along left 8, down 3, 1, 2, 3, 4, 5, 6, 7, 8, down 3, 1, 2, 3. And because the orientation's the same, it would stay like that. Now you can use left and right, up and down, whatever where it is. Or you can say move on the x-axis, +4 or -4. Negative being to the left, positive to the right. And same with the x-axis, and so on. So you can do it in a forward direction, as I say, mathematically. You tell them what to do. Now, the reverse direction is saying, there's the answer, tell me what happened. So you pick any point. So we used A previously, but let's have a look at C. So let's make sure everything lines up nicely for us. Now, so C, this point here, what happened? We went X first. So let's get my camera straight for you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4. So did I move at 10? I don't think I did previously. So let's have a look here. So we went 10 and we went 3. Maybe I did it incorrectly here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I did. I moved at 10. So the A, you go backwards. So that's translation. Anytime you move left and right, up and down. And notice the orientation doesn't change. That's a rotation. skill. So that's how you do that. Big, large blocks, paper in the classroom. Next is reflecting a shape. You know, that's like we're in the mirror. The left appears to be right and so on. That's called a lateral, okay, left and right, inversion. So in a mirror, you notice, and the same with you, that if this is the shape and the reflection, in a sense, lives in the mirror, let's look at this point here. So it's 1 away from the mirror and it's at that level. Well, the reflection's still going to be 1 away from the mirror, but at that level. And each point, that's 3, and that's 3. But then notice, it's as though it is now, this is facing to the right, or slanting to the right, and this is slanting to the left. But it really is moving in a consistent way from the mirror point. So that's 1, that's 1. This point over here, for example, on my left where my pointer is let's go, it's 1, 2, 3, 4, 5 and a bit. So this should be over here, 5 and a bit, and it is. And similarly, so you put all the dots of the shape, the corners, and you plot them and then rejoin. So reflection is not difficult. It becomes a little bit tricky if we don't make the reflection necessarily up and down. Is it on an angle? And you'll see some of those problems. But the principle is the same. So reflection, you have the same distance and same plane, and notice it's perpendicular to the reflection. So if the reflection angle was down that way, for example, sorry about that, on the angle, you would make sure that you're measuring perpendicular to the mirror. There's a trick for you. What would you do in the classroom? Well, let's have a look at that. So let's come back here, put that point there, and let's make the y-axis here our mirror. Okay, so and as for that, it'll be inverted left and right. But what it will be it'll be the same distance from. So here we have, it is from here, it is 1, 2, 3, 4, 5, 6. Equidistance, the word you use. So it's on the same plane and it's 6. 1, 2, 3, 4, 5, 6. So it reflects. It's inverted in its shape, but the distances between each of the equivalent points are the same distance from the mirror that is there. It's reflection. Now what about if we had a mirror which was on an angle? Let's say, to make it easy, put it through the origin point, there were x and y axis there. So let's make that at the 45 degrees there. So that is our mirror. And you'd use a line, a piece of string or stick or something, a long skewer or something. So that's my point here. So if I put this on the point there, well, it's going to be equidistance and left and right. So it's going to be like that. And notice that the D is touching my point there. So therefore, here's my line of mirror. So if I make that up, just sort of move that gently, make that there, like this. There's my line. Notice the same, and I would have to say there's my mirror because my F point here and here would have to be the same. So that's going in the forward direction. You give them the mirror, and now you ask them to orientate it. Going in the reverse direction, what would you do? Well, sorry to mess it up a bit. So there's my, it's rough, I haven't done it exactly, but you would equidistance between those 2 points. Well, you can make the equidistance. So what is the distance between those 2 points? And we put a dot here. There's a point. And we say, what's the distance between those 2 points? Halfway, and we put a dot there. So by putting these dots on there, and that's a touch point, we then can line up my here and work out what it is in reflection. So going backwards is, here's the answer, where's the mirror? Going forward is, here's your mirror, now place it. And both of those are using the concept of lateral inversion, left to right, but also it is equidistant from the reflection line. Okay, next one is rotating. And in rotation, there's the concept of clockwise and anti-clockwise, or counterclockwise as it's sometimes referred to. So let's have a look at this. If you did a quarter turn, now what's a quarter turn? How many degrees? That's important. I think quarter turn, whole turn is 360. Remember our angles. A quarter turn would be 1/4 of that, 90 degrees. So if we measure this object 90 degrees here, and we twisted it to the right, then would it be the same? Yes, it would. These lines here, if we look at here's our vertical, and we twist that to the right, 90 degrees? Answer is no, it would not be. This angle would now be over here. This little rectangle would be on that angle, 90 degrees to the right. Similarly to that, the outside shape would be the same. However, the inside rectangle would be different. And the outside shape would be the same, but the angle would be different through that. So in rotation, you have to specify two things. Its direction of turn, clockwise, anti-clockwise, and its amount of turn, the number of degrees. And there's a number of problems with that. So what's this skill developing? This skill is developing manipulating space and geometry, shape and space. And we're giving some boundaries, some language, and some markers for students to get this manipulation. Now, this is in 2D shape. Now 3D is another whole world, isn't it? So understanding the 2D, or the shape on a page, on a flat surface, so to speak, then they can start to manipulate shapes and see shape, space, amount, and so on. So you're giving them the tools to enable to actually understand it, to describe it, and to manipulate that in their minds. Here's some rules. This is probably a little bit complex. Some people might find it useful, but it's really, having a look at this video, it shows you, okay, now let's go rotation, but on our Cartesian plane. So what would that look like? And I will on that. So for example, we've got something here, and we're saying, let's rotate this shape clockwise to the right, 90 degrees on this, about this plane. So we have a look at that point, and so where are we rotating it? We're rotating it from the midpoint here. So if this was a, where would it end up? What would it look like? Now it's not actually helpful, I don't think, because it doesn't have point A, B and C on it. But let's do a little mental gymnastics. So we're rotating about here. So where would this point end up? Well, it would go rotate 90 degrees here. So it would turn as though that's my axis. Another way of thinking about, put a pencil in the middle, okay, and rotate things around that. If the Cartesian plane stayed fixed, and these shapes were actually on a piece of plastic that could be spun around, and you put your point on here and you spun the plastic around, where would it end up? Well, this point here, they're describing here, to give an example, is that this is 1, 2, 3, 4, 5 x and 3 y. Hence it's how it's described there in the brackets. So what would it look like after it's rotated? And it would be down here, which is 1, 2, 3 x. Still on the right hand side, so it's positive, but it's underneath the water, so to speak, on the y-axis, so therefore it's minus 1, 2, 3, 5. And they're demonstrating that we've actually, look how we've inverted the numbers and put a negative sign. Now that might be a short sort of how to get the answer by knowing that, and that relates to the previous slide that we had there. But really, it's more, for me, it's more important for the students to understand what is going conceptually and to playing with things. How would you use this? Well, what you do is you get the shapes and you get objects and you move them around, and that physically manipulate. Now, if you do anti-clockwise in the same way, if you've had a bit of plastic that this blue one was on, and you had and you rotated it to the left counterclockwise or anti-clockwise 90 degrees, it would go from this quadrant here over to this quadrant here. But it also, not only did it move there, it would actually spin at the same time. So there's a couple of examples to prove or confirm that little table that we saw previously. In the same way, if we did 180 degrees, now it wouldn't matter if it was clockwise or anti-clockwise because it's the same, because you're splitting the circle in half. So it's orientation. Now I think that's probably a bit easier to understand, that the point would be pointing to the right here and the point would be pointing to the left there. But describing the coordinates, it's gone from positive, positive to negative, negative through that. Again, what would that look in the classroom? Let's go for our little L shape again, or upside down L. So we're going to rotate it. Now let's make it easy to start with. Rotate it over the point here on the origin, and we're going to rotate it on B. So first of all, we need to know direction and amount. So direction, let's go clockwise, let's go 180 degrees. So if I rotate by, in a sense, putting a point there, turning it round, I've turned it clockwise 90 degrees. Notice the rotation point stays the same. And the next one is I go further 90 degrees, I go here. So it starts off here, and so in the forward direction, in a sense, we tell them what to do, and it'll end up being here. And notice this looks symmetrical, doesn't it? Because it's 180 degrees. So that's a simple rotation the same way. Let's choose, however, a different point. Let's choose point A. So point A is over here, and we're going to rotate it the same, clockwise, 180 degrees. So the point of rotation stays the same. So let's leave that image there and get my bluey, which is the same, and I'm going to rotate it 90 degrees, this way, 90 degrees, it went there. So because I chose a different point of rotation, it ended up in a completely different position. So that's not say go forward. In other words, you give the instructions and you complete the problem. This one here would then go in reverse. So first question is, what's it rotating on? Well, you look for where the common point is. And the common point in this problem is A. So it's rotating on A. Now, is it rotating clockwise or is it rotating anti-clockwise? Well, to go from there, you say, oh, it's gone clockwise. But you know what? It could also have gone anti-clockwise. It's interesting, if you clockwise rotate 180 degrees, it's the same as anti-clockwise rotating 180. But if you clockwise 90 degrees, it's as though you went anti-clockwise 270. Because they all add up to 360 in the end. So the first thing is to do about where's your point of rotation, and then it's the amount of rotation that is there. So and the other thing you might want to do is you put a point on there and you rotate around that point. Yeah, that was a 90 clockwise, wasn't it? Around this point here. So the point could be anywhere on the shape, but using corners is a much easier way of doing things. So then, of course, you go for those shapes and you get some more complex things. Get big chunks in here using symmetry areas, for example. Use that, or symmetry. It would flip over like that if that's a symmetry in the reflection line. Rotate on a point E. Move it around here and so on. So all those different things you would use in the classroom and get them to manipulate this to develop a concept of shape and space. The other concept you're asked to examine is scale. Now, interesting, scale in 2 dimensions. Now, if you have a line, for example, or a measure using a map perhaps, and you read the map, and on the map it's actually physically in front of you, it's 2 centimeters long between these 2 towns or cities. So that obviously to you, that is not 2 centimeters away, is it? You then look at the scale of the map and you see that 1 centimeter equals 100 kilometers. Easy. 2 centimeters, 200 kilometers. Perfect. That's scale. Now, scale is used so that you can have large things be condensed to smaller things, but you keep the proportion the same, for example. Now, in 2 dimensions, as here, we've got 2 dimensions. So now we're talking about area, aren't we? So let's have a look at shape A and B. Well, A is reduced to B, and I think since Microsoft Word and other Microsoft programs, you understand that. You grab the handle of your object, for example, and you can use the handle and you can make it bigger and smaller. But it keeps the proportion the same. So to work out a scale going forward or going backwards, we really have to look at the relative proportion. So let's take a point here. So I'm going to choose the point B, and it's not point, sorry, a line, B to C. So B is in the large shape A is 1, 2, 3, 4, 5. B to C in the shape B, the smaller one is 2.5. Oh, right. I've gone down from 5 to 2.5. What's my scale? Well, my scale is obviously it's 0.5 scale. You've reduced it. So what the diagram is perhaps trying to say here is using fractions to indicate proportion. So the scale in this one is 2:4 here, or half here. So what it is you choose a large set of units, D to C in this example, and they use D to C in there. So whereas I use B to C here. Now the proportion will stay the same. Now it's 2D, therefore if you've halved on one dimension and halved on one dimension, you notice now it is a quarter of the size, because it's half times a half, because area is length by width to that sort of shape. Let's forget that it's got a little corner cut off for the moment, but it is, you've reduced it in half in one dimension, so half L times half W, and therefore it's 1/4 the LW, the original. So that's what it does. Now in reverse, of course, if you had a small scale like your map, it's going to increase 2 dimensions fourfold if it increased. If it was 3 dimensions now, a volume issue, and the scale was half. So therefore it's a half times a half times a half. It's 1/8. So if you halve a side measurement and do that proportionally on a volume situation, you've now made it 8 times smaller. So understanding those manipulations with scale are some of the problems that you'll talk about. Understanding that's bringing the geometry into the third dimension. Let's go on to the next one. Here's some little ideas that illustrate that point here. I'm going to put myself out of the way a bit more over here. So using that scale, and you're used to it in terms of maps and so on. And what we're shown to illustrate here is that the ratio 1:10,000 is consistent. So if 1 centimetre is 10,000 on the ground, it's your map scale, then 5 centimetres would obviously be five times the 10,000, and it would be therefore 100,000 in this sense. Sorry, not 10,000. 10,000 over on the left-hand side, and it's got 20,000 on the right, not sure, or 200,000 on the right, so not sure why the PowerPoint, I didn't write this one. But can you see that the scale is consistent? That's the takeaway, and in proportion. The other one here has got nets. If you've done early years, you'll understand what nets are. Nets are the shapes, or the lattice sometimes it's called, that create these 3D shapes. So understanding to students that the 3D shape is made up of sides of which can be represented by nets, and it also helps them understand the concept of surface area, because that's what essentially what nets or lattices are about. So symmetry, last one we're going to cover. Pretty easy, I think, symmetry. You know, it's the line, it's in the sense like is there a line where it's equal on each side? So, you know, there's a number of things to talk about in terms of symmetry. Symmetry of regular polygons or irregular polygons, and you can get different lines of symmetry. And I think you get them, how do you do this in the classroom? You get them to play with this stuff. And it's all about manipulating shape and space in the classroom. And letters would have symmetry, for example, and some letters wouldn't, because you use their everyday examples from their world for this. Do you see a pattern of symmetry here? It's a decathlon. Deca, 10. decimal, 10. That's sort of the root prefix words. So you have 10 sides, 10 lines of symmetry. There you go. Pentagon, 5 lines of symmetry. Penta, 5. Quadrilateral, 4. There's a pattern going on. Maths is full of patterns. It's fantastic. So easy when you get to the bottom of it, isn't it? So it talks about perspective, and again that's getting students to conceptualize shape and space. In other words, if here's a stamp, it makes a key, which one would the stamp make? So you've got to manipulate this in your mind. Okay, that's at the bottom. That's going to be when it stamps. Is that going to be on the left or the right? What's your answer? That at the bottom, it's going to be on the left. That at the bottom, that's on the right. That's no good. Okay, that's not at the bottom. I'll have to turn that shape off. That one's on the left. Well, in fact, that's a candidate. This one here is exactly the same as the first one, the third one. And the last one we can't see, it's cut off. And that's exactly the same as the first one as well. So its answer is this one here, B. And that's about manipulating shape and space. And the kids will need practice for that. You'll need practice for that. Maybe you're not a great map reader or direction finder. Well, you're going to improve. That'll be interesting. Okay, then you get them to have a look at complex ones and find out what it would look like. Not going to give you the answer. You work it out. Pause the video, work out which one it is. And here, if you looked at things in different directions, what would it look like? So there's some sample questions that perhaps you find on standardized testing, for example, about what it would look like. So if Alex, let's do this one here. If you looked from that, so there's pile of 3, and a pile of 1, and that's going to be in that 3 is behind that 1 as a 3 and 1. So I'm looking for a 1 and a 3 first. So obviously the squares are out of block. So it is 1 here. So which is view of the cans? Oh, right. So they're talking about from above. Right. Don't think the question's real clear. So which would I look like? I would obviously from above, it would be D. If I looked at it from that view, different perspective. Okay, so I hope you've enjoyed some of those things going through, and you, as like all of them, you then now go into your Moodle page and start that journey on geometry.